Okay, let's look at a consequence of this. Okay, we start off the example of a string that's tied at both ends. Okay, so this is one end of the string and this is one end of the string. So the two ends. Now, what we are looking at are the standing waves that we can have oscillating at that string. At the lowest frequency, we are going to have one node at both ends. We will have nodes at the ends because the ends are fixed. So the string has nowhere to go. So because it is tied here and tied here, it has nowhere to go, we have nodes. So at the lowest frequency, we'll have nodes at both ends and no other nodes. So halfway between the nodes, we'll have what we call the antinode. And remember, the distance between two nodes would be half of the wavelength for that particular wave. So actually, we can measure the wavelength by just measuring the length of the string. If we know the length to be L, that's from here to here, then half the wavelength for that particular case is L. So we can directly measure the wavelength. Now we know the wavelength. If we know the speed of the wave, we can find the frequency. Or if we know the frequency, we can find the speed of the wave. Remember the relationship between wavelength, speed, and frequency. Wavelength is V over F. Now that we know the wavelength, if we know one of these two, we will know the other one. Okay, now an example of something like this that will have a standing wave pattern like this would be a guitar string. Now let's focus more on these standing waves. This particular standing wave has a high amplitude oscillations because the string has the freedom to move quite a distance from here to here. What is interesting is that string can oscillate at other frequencies with standing waves. For example, we have this situation here. In this case, we still have a node at both ends because the nodes are tied, but we have a node midway through the string.